Viewers, today we'll be looking at applied mechanics for engineers. We have a question on the board. This is a balloon, and at point A, it is anchored by a cable AB, and then at this same point A, it is anchored by another cable AC. That is from here to here, and at the same point A, it is anchored by cable AD. Alright, so it is anchored by three cables AB, AC, and AD. So it is anchored by three cables: cable AB, cable AC, and cable AD. Right, and those are the dimensions given to us. Okay. So observe the diagram. Observe that diagram closely. Observe it closely. Alright. Okay. And then you see this is the z-axis. Over here is the x-axis, and up there is the y-axis. Okay, so let's look at that question quickly. It says three cables are used to tether a balloon as shown. Knowing that the balloon exerts an 800 Newton vertical force at A, determine the tension in each cable. So at point A, the weight of that balloon at point A is 800 Newton. So let's quickly look at that. You draw the free body diagram, and this is the free body diagram. Observe it closely. That is the free body diagram. And with the aid of the free body diagram, we can solve this question. With the aid of the free body diagram, we can solve the question. So this is the weight of the balloon, 800 Newton, acting at point A. Then you come to cable AB. This is the unit vector, lambda AB, and then the tension AB. Then the vector tension force AD, and the unit vector, lambda AD. Vector tension force AC, and unit vector, lambda AC. Alright? Okay, so let's solve that question. We then look at the summation of all the forces acting. The summation of all the forces, you say you take resultant. Take the resultant of all the forces. Okay, so the resultant arrow will be equals to sigma F, which is equals to, I'll take the first one there is TAB. So I have my vector force TAB plus, next is TAC, vector force TAC plus TAC plus, the next is vector force TAD plus TAD plus, the next one is the weight that is acting at point A plus the weight acting at point A, which I can call this one equation 1. Now we'll consider cable AB. Consider cable AB. Then I can look for the distance. This distance now is a position vector. So position vector RAB from the free body diagram. Let's go to that free body diagram. Now look, this is the J coordinates. Any movement that goes upwards like this is positive. The I coordinate, anyone that goes like this is positive I. Anyone that comes like this is positive K. So positive K, positive I, positive J. But if I'm coming downwards, if I'm coming against this now, opposite this, that if I'm coming down like this, it is minus J. And then if I'm going like this, it is minus I. If I'm going like this, it's minus K. Okay, so let's come. I do AB now. I'll move. This is the distance, 5.60. I'll move like this. If I come down, I'll have minus 5.60 J. Then I'll move this way, minus 4.20 I. Okay, so I come down like this. From here, I come down like this, minus 5.60 J. Observe, if I come down, it is minus 5.60 J. If I go like this, it is minus 4.20 I. That's this distance from here. If I get here, I move minus 4.20 I. Okay, let's go again. If I come down, it is minus 5.60. Coming down like this, it's minus 5.60 J. Then I go, it is minus 4.20 I. Okay, that's it. So this is minus 5.60 J, and then this is minus 4.20 I. Okay, all right, so that is it. And then if I rearrange it properly now, I'll have minus 4.20 I minus 5.60 J. Okay, that is RAB position vector. Now get the modulus. The modulus is the magnitude RAB, which is square root, using Pythagoras rule, minus 4.20 square plus minus 5.60 square. So this now will be the modulus RAB will equals to square root of, if I find the square of this now, I'll have, this is 17.64 plus, if I square this other one, I'll have, this will give me 31.36. So if I add them, I have RAB modulus as the square root of, adding this now, I have this will give me, add this now, I have square root of 49, which is 7. So lambda AB, which is the unit vector, is the position vector divided by the unit vector, divided by the modulus, okay. So that is it. So this is equals to, my position vector is minus 4.20 I minus 5.60 J divided by 7. If I split this now, I'll be having lambda AB is equal to minus 4.20 divided by 7I minus 5.60 divided by 7J. Okay, so this now will give me lambda AB will be equal to, if I divide this now, I'll have, I'll be having, so this will give me minus 0.6 I minus 0.8 J. Minus 0.6 I minus 0.8 J. Okay, so then I'll look for tension force AB. Vector tension force AB is equals to the original tension force TAB times the unit vector. Okay, so the vector TAB will be equals to original tension force times minus 0.6 I minus 0.8 J. So I put the value of this, that's lambda AB, I put it inside here, then multiply it with TAB. I have minus 0.6 I minus 0.8 J. So if I expand it now, I'll be having, by expansion I'll have, TAB will be equals to, if I expand that, that is minus 0.6 TABI minus 0.8 TABG, of which I can call this equation 2. Okay, this is equation 2. And this other one is equation 1. This is equation 1. Then call this equation 2. Okay, and I say consider, let us consider cable AC. Consider cable AC. I can then look for the unit vector, the position vector. Position vector RAC. Position vector RAC will give me, position vector RAC gives me position vector RAC. Okay, now move until I get to point C. Okay, so let's move. Okay, I'll come down now. Let's move. I'll come down. Coming downwards. From here, I'll move down, get to this point. So I'll move from here, come down, get to this point. And this is with respect to this distance, 5.6. So if I come down now, we'll have minus 5.60 J. That is this distance, 5.60. Okay, so let's move. Come down. Minus 5.60 J. Then I move like this. If I come like this, I have plus 4.20 K. I go then this way to point C, plus 2.40 I. Okay, so I get to this point, I'll move like this, coming this way is with respect to 4.20, come like this, plus 4.20 K, and I go like this. I will move like this, plus 2.40 J. Now you see the direction of the arrowhead. See the direction of this K coming like this is positive. Then when I get to this other point, that is going like this, is also positive I. So from here now, move, that is plus 4.20 K, and I go like this to point C, plus 2.40 I. Okay, so that is it. So I explain again. I move down from here, come downwards. From here like this, I come down. Now that is minus 5.60 J. This is coming down. Then I move like this, plus 4.20 K. That is K. Plus 4.20 K. Then I move like this, plus 2.40 I. Okay, take note. All right. So RAC now will be minus 5.60 J. Then plus 4.20 K plus 2.40 I. Okay, if I arrange it properly, I'll be having 2.40 I minus 5.60 J plus 4.20 K. Okay, this is RAC. Sorry, RAC, which is my position vector. This is the position vector RAC. So this is I, J, and K coordinates. So now if I find the modulus or the magnitude of the vector RAC, this is modulus RAC, will give me, using Pythagoras rule, as 2.40 all raised to power 2 plus minus 5.60 all raised to power of 2 plus 4.20 all raised to power of 2. Okay, so this now will be the square root of 2.40 square will give me, should give me 5.76 plus, now if I check the square of this will give me 31.36 plus the square of this other one will give me 17.64. Okay, so when I add everything now, I'll have, if I add this, I'm having, so if I add this now, I'm having 54.76. So finding the square root now, the square root of this now will give me, square root of 54.76 gives me, this will give me 7.4. This is my modulus RAC. Okay, so I will then look for the unit vector. So unit vector lambda AC will be equals to the position vector RAC divided by the modulus of that vector. This now will be equal to, I'll take that one out. RAC, unit vector RAC is this. Okay, so this is 2.40 I minus 5.60 J plus 4.20 K divided by 7.4. 7.4 is this other one. That's the magnitude or the modulus. So if I split them now, I have that lambda AC is equal to, by splitting this is 2.40 divided by 7.4 I minus 5.60 divided by 7.4 J plus 4.20 divided by 7.4 K. Okay, so that is it. Then lambda AC now lambda AC will be equals to, by dividing this now, have, this will give me 0.3243 I minus, if I divide this other one, I have, it will give me 0.7567 G plus, if I divide this other one, I'll be having, to give me 0.5675 K. Okay, so that is it. So that is tension AC equals to TAC lambda AC. Okay, so now this now be TAC vector TAC equals to vector TAC equals to original tension force TAC times 0.3243 I minus 0.7567 J plus 0.5675 K. Okay, so I just had to substitute the values of this. These are the values of lambda AC, so I just put it inside there. So this is what I have. Now if I expand it now, by means of expansion, I'll have, if I expand this bracket, this will times this, this will times this, this will times this as well. So I'll have, okay, so I'm having TAC, a vector TAC equals to 0.3243 TACI minus 0.7567 TACG plus 0.5675 TACK. Alright, so this is it. Okay, that's when I expand it, and I'll have that. So I can call this one equation 3. Okay, because equation 2, this is equation 2. So that I can call this one equation 3. Call that equation 3. Okay, I'll then consider, I say consider cable AD. If I consider cable AD, I come to the free body diagram. Let's look at the free body diagram. Now let's move from A to D. Let's move from A to D. So if I move from here, from point A, I come downwards. That is minus 5.60 J, and then I go straight to D. To be minus 3.30 K. Alright? So take note of that. I come downwards like this, minus 5.60 J, and I move minus 3.30 K. Okay, come down, minus 5.60 J, then minus 3.30 K. Alright, so that's it. So this now will be RAD equals to minus 5.60 J minus 3.30 K. Okay, so that is it. Coming down like this is minus 5.60 J. Then I move like this with respect to this distance. Move like this. It is going opposite K like this with minus 3.30 K. So that's what I have. Alright. And I can then look for my modulus. The modulus of the vector RAD will be equals to the square root of minus 5.60 all square plus minus 3.30 all square. So RAD will be equals to the square root of find the square of this now. That is 31.36 plus this will give me 10.89. So if I add them now, adding this, then I find the square root. So if I add them now, I have 42.25, I'm finding the square root of 42.25. This will give me 6.5. That is my modulus. Modulus of the vector is 6.5. Now I can find the unit vector. The unit vector is lambda AD. Lambda AD will be equals to the position vector ROAD divided by the modulus ROAD. This will be equal to, okay, so if I take this first one, now this is minus 5.60J minus 3.30K, okay, divided by 6.5. Okay, so if I divide that now, I have lambda AD is equals to, by splitting it, this is minus 5.60 divided by 6.5 J minus 3.30 divided by 6.5 K. So lambda AD will be equals to minus, if I divide that, I'll have, so give me 0.862 J minus, if I divide this other one, I'll have 0.507 K. Okay, so tension AD is TAD lambda AD. So that means vector tension AD will be TAD times lambda AD. Put the value of lambda AD there. That is minus 0.862 J minus 0.507 K. If I expand that now, I have minus 0.862 TAD J minus 0.507 TAD K. Okay, this is the vector force, vector TAD, of which I can call this equation, equation 4. Call that equation 4. This is equation 4. Okay. Alright. I can call this equation 4. This is equation 3. Okay, so the next thing now is to look at the weight of the body, the weight of the balloon. So look at the weight of the balloon. Consider the weight of the balloon. Weight of balloon at point A. Observe here at point A. We are looking at the weight of the balloon. We are told that the balloon exerts an 800 Newton vertical force at A. And I told you that the weight of a body must act vertically downwards. So it's acting down like this, which will be minus 800 J. Since it is going down, if it's up, it's plus J. So it's coming down, it will be minus 800 J. It means that W, the vector W, will equals to minus 800 J. Okay, of which I can call this one equation 5. Now substitute equation 2, equation 3, equation 4, and equation 5 into equation 1. So if I substitute into equation 1, I'll be having that my vector sigma F will be equal to that is the resultant arrow, which is sigma F, will be equal to, okay, first put equation 1 there. I'll be having, so I have minus 0.6 TAB I minus 0.8 TAB J. Okay, then I'll then put equation 3. Equation 3 is 0.3243 TACI minus 0.7567 TACJ plus 0.5675 TACK plus, I then put equation 4. Equation 4 is minus 0.8 62 TAD J minus 0.507 TAD K plus, I can then put equation 5. Equation 5 is minus 800 J. Okay, so now I'll arrange them properly. That sigma F will be equals to, taking all the I coordinates. Let's take all the I coordinates, I, and okay, I think these are the only I coordinates. So let's take all the I coordinates. This is minus 0.6 TAB, and I take this one plus 0.3243 TAC. I call this I. So I look at this other one. This is plus 0.8 TAB, then minus 0.75667 TAC. This is J coordinate. I took it. Take this other one, which is J coordinate. I'll take it as well. Then I'll look for another J coordinate. This is a J coordinate. I'll take it. This is minus 0.862 TAD. Then I'll look for the next J coordinate, which is this, minus 800. Minus 800. I'll call this J. Plus. Then I can look for K. Look for K. This is K coordinates. That will be 0.5675 TAC. Then I'll look for another K coordinates, which is this, minus 0.5507 TAD. Okay. Then I call this K coordinates. Alright. So this is I, this is J, and this is K. So this now is sigma F equals to sigma Fxi plus sigma Fyj plus sigma Fzk. Okay, so if I separate all of them now, sigma Fs is this, and this is the I. This other one is I as well. Okay, then sigma Fy is the whole of this. That is the J coordinate. This is J coordinate. Sigma Fz is the whole of this. This is K coordinate. This is K coordinate. So by comparing them now, comparing the coefficients, I have that sigma Fx will be equals to, write this one out, that is minus 0.6 TAB plus 0.3243 TAC. Okay, and the sigma Fy will be equals to 0.8 TAB minus 0.7567 TAC minus 0.862 TAD minus 800. Okay, then sigma Fz will be equals to 0.5675 TAC minus 0.507 TAD. Okay, this is what I have: sigma Fx, sigma Fy, and sigma Fz. Now the next thing I look at is equilibrium conditions. I say equilibrium conditions. Equilibrium conditions is a static equilibrium conditions. Shows us that sigma Fx and sigma Fx is 0, sigma Fy is 0, and sigma Fz is also 0. These are static equilibrium conditions. Okay, so I'll apply it to the three equations: sigma Fs, sigma Fy, and sigma Fz. So that means that sigma Fx is equals to 0 will be equal to, if I write that out, that is minus 0.6 TAB plus 0.3243 TAC is equals to 0. Can call this equation 6. Call that equation 6. Then sigma f y, which is equals to 0, will now be 0.8 TAB minus 0.7567 TAC minus 0.862 TAD minus 800 is equals to 0. Call this equation 7. So I call that equation 7. And then sigma fz, which is equals to 0, will now change to 0.5675 TAC minus 0.507 TAD, which is equal to 0. I call this equation 8. So this is equation 6, 7, and 8. Alright? Okay, then I can solve that. I'll have so this is what I'm having. Okay, then I can start from equation 6. I say take equation 6 from equation 6. From equation 6, I'll be having minus 0.6 TAB plus 0.3243 TAC is equals to 0. Okay, so if I take this one over here, I have 0.3243 TAC equals to 0.6 TAB. So if I divide by the coefficient of TAB now, which is 0.6, I have TAB equals to 0.3243 divided by 0.6 TAC. So tension AB now will be equal to, if I divide that, so this will give me 0.54 TAC, alright, of which I can call that equation 9. Okay, and I go back to the other equations. If I take this one, take this equation 8, if I take equation 8 out, take equation 8, I'll have, say from equation 8, I'll be having 0.5675 TAC minus 0.507 TAD is equivalent to 0. So if I carry this one over here, I have 0.5675 TAC equals to 0.507 TAD. So if I divide by the coefficient of TAD, I have that tension AD equals to 0.5675 TAC divided by 0.507. And if I divide that now, I'll be having, so this now is TAD is equals to 1.12 TAC. I was using my calculator, I approximated it to 2 decimal places. So I had 1.12 TAC. I can call this one equation 10. Okay, so I will substitute equation 9 and equation 10 into equation 7. Okay, substitute them into equation 7. This is equation 7. This is equation 7. So in place of TAB, I will substitute equation 9. And in place of TAD, I will substitute equation 10. And this is what I'll have. So this is what I'll have. I'll have 0.8 times, put the value of that TAB there, that is 0.54 TAC minus 0.7567 TAC minus 0.862 times 1.12 TAC minus 800 is equivalent to 0. Okay, so if I expand the brackets now, by expanding this bracket, I will multiply and I'll have, this will give me minus 0.432 TAC minus 0.7567 TAC. This is minus, to give me 0.965 TAC minus 800 is equals to 0. So if I add them now, if I add everything there, that will be okay. So remember, this is what we had initially. This value here is what we extracted out as this. Finally, using the equilibrium conditions, we arrived at this, minus 0.8, okay, equals to 0. And when I substituted them, the value of TAB and TAD inside this equation, I arrived at something like this, minus 0.8 times, okay, value of TAB, I put it there, that is TAB 0.54, I put it inside there, okay, then TAD is 1.12, put it here. When I multiply now, I'm having something like this. So if I add everything now like this, I'll have my calculator. Do that with your calculator. You'll be having, give me minus 2.1537 TAC. Okay, minus 2.1537 TAC minus 800 is equivalent to 0. Okay, so it means that if I take this value over here, I'll have minus 2.1537 TAC is equals to 800. I'm taking minus over here to change to positive. So I have minus 2.1537 TAC equals to 800. If I divide by the coefficient of TAC, which is this, I'll have TAC is equals to 800 divided by minus 2.1537. This will give me minus, to give a negative value, so this will give me minus 371.45 Newton. Okay, therefore tension in cable AC is minus 371.45 Newton. I'll then substitute. It says substitute tension AC equals to minus 3.771.45 Newton into equations 9 and 10. So substitute them into equation 9 and 10. So equation 9 is TAB equals to 0.54 times TAC. So this now will be 0.54 multiplied by minus 371.45 Newton. That will give me a multiply. I'll be having, so this is 200. This is negative 200.583 Newton. Okay, then that is tension along AB is this. All right, so I have the value of tension in AB as minus 200.58 Newton. Minus 200.58 Newton. So I'll look at, say, let's look at equation 10. Equation 10 is TAD equals to 1.12 TAC. This now will be equals to 1.12 multiplied by the value of TAC is minus 371.45. So if I multiply them, I'll be having minus, if I multiply this now, I'll have minus, so this is minus 416.024 Newton. Tension in AD. Okay, so that is it. So at this point we have gotten the tension forces. Therefore you say tension AB is 200.58 Newton. If you neglect all the negative sign there, neglect the minus sign, then tension AC is 371.45 Newton, and tension along AD is 416.02 Newton. Okay, so those are the tension along the cables. Tension along the cables is this. Alright, at this point we have come to the end of the lesson. Thank you. And please, whenever you are learning these particular lectures conducted by me, please ensure that you have your book and your pen and you are taking down notes. Because this is not a movie, but an educative content. Please, you're supposed to take your pen, your book and your calculator and solve with me. Alright? Okay? Please take your pen, your book and solve with me. You'll be sure of what we are doing here. Alright, thank you. So this is it. We have come to the end of the lesson today. God bless you. Thank you.